Hello lovelies, in this video the brilliant Charlotte is going to be going through my predicted paper for AQA AS Chemistry paper 2. So there are lots of important things for you to look at in this paper. Not only how you can interpret what the examiners, what I am actually asking you to do in a question, because sometimes it's not always obvious, but how you can structure your answers to clearly show the examiner you know exactly what you are talking about. If you haven't had a go at this paper already, what I want to do is to pause after the question comes up, have a go at it yourself on a bit of paper, and then play and we can go through the answers together.
Hello and welcome to today's paper 2 for AQA AS Chemistry. This is Charlotte here and I'm going to be here to help you through this paper. So section A here begins with a chemist carrying out an investigation on the equilibrium system shown below. So we're given some information here and we're asked to predict what changes might happen on the position of equilibrium and the rate of the backward reaction when we do a couple of changes. Okay, so here we can see that the temperature we are going to keep the same, the pressure we are going to also keep the same, but we have a difference here. Initially we used a catalyst, but now we do not use a catalyst. So here we need to predict those changes. So for the position of equilibrium, we're going to say that there is no change. And the reason why there is no change is because equilibrium doesn't do anything to affect that position of equilibrium. It's not going to shift it to the left or to the right. All that it's going to do is to speed up the rate of the forward and the backwards reaction, but by the same rate. And that's going to give us our explanation for part 2. So when we do not use a catalyst, the rate of the backward reaction is going to decrease. And the reasoning for that is, again, when we have dynamic equilibrium, the rate of the forward and the backwards reaction are equal. Okay, so if we change this rate by, say, not using a catalyst, then that reaction is going to take place slower of both the forward and the backwards reaction. Perfect. Let's try the next question. Okay, so the chemist mixes together 2 times 10 to the minus 3 moles of X and 4 times 10 to the minus 3 moles of Y in a 1 decimeter cubed container. At equilibrium, the mixture contains 3 times 10 to the minus 4 of X, so we can see that the amount of X has gone down. Now we're asked to calculate the equilibrium constant, Kc, including units, if any, for the equilibrium. And we want to give our answer to 3 significant figures. So first things first, let's write down the equation that we had on the previous page, because we need to use that here. So because this is an equilibrium question, I'm going to use my ICE method. And I use this just to help me lay out the information and get everything that I might need. I like to separate the products and the reactants with like a little double line just so that I can clearly separate them in my head. And I'm going to start now by just filling in the information from the question. So I know that I've got 2 times 10 to the minus 3 of X, so I'm going to fill that in. I also know that I have got 4 times 10 to the minus 3 of Y. It's important to note that we have a 1 decimeter cubed container. That's important because as it's 1 decimeter cubed, that means that the moles, the number of moles, is actually going to be equal to the concentration, because concentration is moles divided by volume, and in this case the volume is just 1. So in this specific case, the moles we can use as the concentration. So I think it's fair to assume from what they've said that we didn't start with any Z at all, so we're going to put a little 0 there. And we're told that at equilibrium the mixture contains 3 times 10 to the minus 4 moles of X. And we're told that at equilibrium the mixture contains 3 times 10 to the minus 4 moles of X. Okay, so we can see there that it's gone down. And this is where our ICE table comes into it. So it has gone down by a certain amount. We need to work out, well, by how much? And the change here is 1.7 times 10 to the minus 3. So that's how much it has gone down. Now we can use that change to work out the amount at equilibrium of both y and of z. So all of the reactants are going to go down by that factor and up by the same. So an important thing to notice here though is that we have 2 moles of x but only 1 mole of y. That 1.7 times 10 to the minus 3 that it has gone down is representing 2 moles of change. But y is only 1, so what we want to do there is to halve that amount and to instead now subtract half of 1.7 times 10 to the minus 3. So that here is going to be 8.5 times 10 to the minus 4. Now that is what it is going to go down by, which is going to leave you with an equilibrium amount for y equal to 3.15 times 10 to the minus 3. Now over on the other side, because those are the products and the products are what we're making, it is going to go up, and because it is 2z, just like there were 2 x's, it's going to go up by 1.7 times 10 to the minus 3. So 0 plus that amount just leaves us with 1.7 times 10 to the minus 3. So we have all of our equilibrium amounts. It's worth just pointing out there that all of those relate to the moles. If this was a different type of question and say the volume wasn't 1, we would then want to work out the concentration to find Kc. But because this is just 1 decimeter cubed of volume, the moles is the same as the concentration. So now we've got this, what we can do is to say, okay, so Kc equals, and it's the concentration of the products to the power of their moles divided by the concentration of the reactants to the product to the power of their moles. So the equation for this case would be the concentration of Z squared over the concentration of X squared times by the concentration of Y. And in this case, we will put in the right numbers. So we've got 1.7 times 10 to the minus 3 squared all over 3 times 10 to the minus 4 times by 3.15 times 10 to the minus 3, and oh, I've forgotten to square this, squared. Okay, so now that we have that there, we will put that into our calculator and out will pop an answer, and to 3 significant figures, which is what was stated that we wanted, I get 10,200. So my Kc is 10,200. And of course here we want the units as well. And to work out the units, we go back to that formula that we had for Kc. But instead of inserting the numbers, we're going to insert the units. And we will see if there's anywhere where we can cancel things out and simplify. This basically turns into a little bit of algebra. So here I can see that on both the top and the bottom is moles per decimeter cubed squared. So I'm going to cancel those out, and that leaves me with Kc equals 1 over moles per decimeter cubed. Because both of those are on the bottom of a fraction, we don't really give units like that 1 over something. We want to rewrite it, and the powers of anything on the bottom of the fraction, their sign is going to be changed. So at the minute it's like mole to the power of 1, we're going to make that mole to the minus 1 and dm cubed. So the answer to this, the units, would be mole minus 1 dm cubed. Perfect. So here a 25 milliliter sample of NaOH is titrated to the endpoint with 15 millilitres of a 0.5 molar HCl solution. What is the molarity of the NaOH solution? Now, of course here it's the typical HCl, acid plus hydroxide, so a base. So an acid plus a base makes a salt plus water. It's that classic reaction again. The important thing is that we understand that it's a one-to-one reaction. So that means that the amount of moles that we have of HCl will be the same as the moles of NaOH. So for that reason, we can say that the concentration times the volume of, say, the HCl is going to be exactly the same as the concentration times volume of the NaOH. Because of course concentration times volume gives you the moles, and we know that the moles of HCl is the same as the moles of NaOH. So here, if we put in the relevant numbers into this, we will be able to rearrange it to find the molarity of the NaOH solution. And let's say that that is this one here. So if we say that the 2s are relating to the NaOH and the 1s are relating to the HCl. Okay, so C1, what is the concentration of the HCl? I can see it as 0.25 and the volume of it is 15 millilitres. Because these are all proportional and the units are the same, I'm just going to leave it as 15. So then on the other side, obviously we want to find the concentration of NaOH and the volume of NaOH is 25. So here we've got this, we're just going to rearrange this now and I get 0.25 times 15 over 25 and that is simply going to give me 0.15. So the concentration or the molarity of NaOH solution will be 0.15 molar. Okay, so titration experiments use equipment with a measurement uncertainty. The uncertainty of the pipette which was used is plus or minus 0.04 centimetres cubed, while the uncertainty of the burette is 0.05 centimetres cubed plus or minus. So calculate the percentage uncertainty for the burette titra value of 25 centimetres cubed and the pipette volume of 15 centimetres cubed. So generally speaking here, what we have is it is the uncertainty over the measurement times by 100. Generally speaking what we have here. Now we've got to be careful of something though, because sometimes certain things that we measure, we need to multiply the uncertainty by a number. Okay, and that is going to happen in one case here, particularly in that burette measurement, so the titra value. So with the pipette, pipettes are pretty straightforward, okay? So for the pipette, when we're working out the sample volume, so pipette sample, all right, the uncertainty just is what it is. It is just 0.04. We just take it in, we squirt it out, great. That's our one measurement that we are actually taking there. And we divide it by the measurement, which was 15 for that, and times it by 100. Now, when I do that, I get a number equal to 0.27%, and that is our uncertainty in the pipette. But we've got to think a little bit more for the titra. And think about how we do titrations as well, don't we? There's a few elements to it. You first take your little burette. Here's my really rubbish diagram, if you excuse me. And you have a certain amount to begin with, don't you? And you take the initial volume. So there's one reading of volume. Then you do some drops, don't you? And then you judge. You make a judgment, don't you? Oh, that's it. That's the drop that changes maybe the colour of the indicator where you just had that neutralisation. And then you judge. Yeah, that's the drop. But then also you then take another measurement, don't you? You look at this and you say, okay, cool. I've now got, again, this another measurement I need to take to then be able to dictate what the titra was by subtracting the two. So here, what I'm getting to here is that the burette's measurement, so the burette titra value, if we think about the uncertainty for that, yes, we've got this 0.05 plus or minus, but there's three places where we could go wrong. The initial measurement of the volume, the final measurement of the volume, and also that judgment of the endpoint to the nearest drop. So for that reason, we're going to times this by 3 and then divide it by the measurement, which is 25, times it by 100, and I end up getting for this a value equal to 0.6%. So that is our uncertainty in that titra. So I think that's a tricky one. Obviously, initially you just need to know how to calculate percentage uncertainty. If you're at all unsure on that, then I would really recommend that you start memorising this equation here. But then it's just remembering, isn't it? Oh, could there be other factors at play? How many measurements do I actually take to measure this? So something like the change in temperature, you would times it by 2. Because you take an initial temperature and a final temperature and subtract, don't you? But yeah, lots for you to think about there. Let's have a look now at the next question. So here we're asked to draw the structure of E, pent 3-ene-2-ol. So before worrying about the E bit, I would first just draw out the pent 3-ene-2-ol. So here, if I was to draw this, I know that there's 5 carbons in a row. So I would start by doing that. And I know that on the second carbon, I have an alcohol group. And I know on the third carbon, I have a double bond. So what I've got here is pent, because I've got 5 carbons, 3-ene, because that's where the double bond is, 2-ol. And I know that I now need to fill in all of the relevant hydrogens there as well. So I'm going to put 3 hydrogens around this carbon. Remember, each carbon has 4 bonds in total. And then here we have filled it in just lovely. Okay, so now they want us to draw the structure of the E isomer of this. And the way that I like to do this is to always have it with a centered C double bond in the middle, and then kind of make it look a bit like we would make ethene look. So looking at what I've drawn here, I can see that on either side of our molecule, I can see that on either side of the carbon belonging to the carbon-carbon double bond, I'm circling here the 2 different groups that each of them have. And so what I would do is I would abbreviate those, and you can sort of still draw them out big and sort of in the same format we see there, but it's absolutely fine also just to draw it slightly more shorthand. But of course, so long as you can see what we can see, then it's great. So the E isomer of this, E means that the significant groups, the similar groups, are going to be on opposite sides. And here, of course, there's an H on each side. So those H's we're going to put on opposite sides because that's what the E isomer has. And this here is our final answer. Okay, so we've got the H's on opposite sides, we've got a CH3 on one of the carbons, and on the other carbons we have this CHOH-CH3. So I will draw that into this little bit here. Never quite enough space in these exams, but you'll be just fine. Make sure that each of the little bonds are attached to the relevant atom that it is actually bonded to be able to get full marks here. They haven't said it has to be given a skeletal formula or displayed or structural, so any of these would be acceptable in the answer so long as it is correct. Okay, so the above compound was analysed using infrared spectroscopy. The infrared spectrum contained a broad absorption in the region of 3,230 to 3,550 centimetres to the -1. What does that broad absorption indicate? So if we go to our data sheet, in the data book that we get along with our periodic table, we will see a little table of values for the infrared spectrum. And a broad absorption at these values represents an OH group being present. And we can see that that is true because of course there is an alcohol group in this. So next we want to draw one of the structural isomers for the above compound that is acyclic and contains a different functional group. Now acyclic is important because acyclic means that it is not cyclic. It'd be very easy there, I think, to get confused, see the word cyclic and to think, oh great, I need to do a ring. Acyclic actually means the opposite. We do not want a ring. We can also see in this question that we need to have a different functional group, so we need to go from there as well. So let us have a little go at thinking what could be an alternative functional group for this. So I think a good idea could be maybe like a ketone group. So if we were to have a go at that, let's imagine we still have the 5 carbons, don't we? Because it's an isomer, so we've got the same amount of carbons, hydrogens and oxygens, they're just going to be rearranged differently. Let's imagine, say we have a double bond O on there. And let's have a go at filling in all of the hydrogens that will have. Now that second carbon won't have another hydrogen because it already has the 4 bonds that it needs to be fully bonded. And then the rest of the places we have in the little hydrogens, and we're good. Okay, so let's check, is this actually a structural isomer? So it's acyclic, it doesn't have a ring, and it does have a different functional group. It doesn't have an alcohol group anymore, instead it has a ketone. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So we have got C5, H10, and an oxygen. Now, if we do the same with the original, structure from part 3.1, I can count through that all again, and I can see I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens. So I do have C5H10O. So that would be perfect. So you could draw it in this structure that I've got here, or you could also write it in the skeletal formula with a little double bond O there, and both of those would be perfectly acceptable as your answer. Excellent. Well, let's have a look at the next page. Okay, so the structural isomers which were drawn in 3.3 have a lower boiling point than E-pent-3-ene-2-ol. Explain why. So this E-pent-3-ene-2-ol is of course an alcohol, whereas we have just drawn a ketone, haven't we? Now, what an alcohol has that a ketone doesn't are those OH groups. And OH groups can form hydrogen bonds. So we can say that the alcohol has OH groups which can form hydrogen bonds. And those hydrogen bonds are stronger than the intermolecular forces that the ketone will have. So hydrogen bonds in the alcohol are stronger than the ketone's intermolecular forces. And so therefore it is going to take more energy to break those bonds, which links to those higher boiling points. So more energy needed to break bonds, which means higher boiling point. Perfect. So question 3.5 is very similar. Similar idea. Again, we're asking to compare boiling points. So we've got two different compounds. They have similar molecular weights, but they have different boiling points. We have compound A and compound B here. And we're asked to identify the compound with the higher boiling point and to explain why it has that higher boiling point. So the answer to this one will be B. So in this case, we get something very different to the last bit, 3.4. We have the same functional group between them, but there are some other differences, okay? So for this one, what we want to do is to compare how compound A is different to compound B. And compound A, although it is an alcohol, it is a tertiary alcohol. And that is a really important point. So because it's a tertiary alcohol, we can say that it has more steric crowding around that OH group. And that in turn is going to have an effect on its ability to form hydrogen bonds. So although they still both have alcohols, they don't both have that same ability to form hydrogen bonds. So that tertiary alcohol, it has more steric crowding around the OH group, and so therefore there's going to be fewer hydrogen bonds made. Whereas if we compare it to compound B, see that one there, we have a primary alcohol, don't we? And because we have a primary alcohol, we can state that we're going to have a lot less steric hindrance around that OH group. So kind of the opposite around the OH group. And so as a result of that comparison and the fact that compound B, because it's a primary alcohol, it has less of this steric hindrance, we can make more hydrogen bonds than compound A. So that there is going to be the determining factor in their boiling points, because compound B has many more hydrogen bonds within it, which enables it then to have a much higher boiling point because more energy is needed to overcome that increased number of hydrogen bonds. So compound B has the higher boiling point, has more hydrogen bonds, and therefore more energy needed to overcome them. Perfect. You see, that one's a 6-mark question, so you do want to be very, very thorough with your answer there. But that's really good work. Let's have a look at the next page. Okay, so this question here is an enthalpy question. We're given alcohol P and we're told that it has a molecular formula of C6H12O. A student does an experiment to measure the enthalpy change of combustion, and combustion of 4.4 grams of the alcohol. So we know the mass of the alcohol is equal to 4.40 grams, changes the temperature of the water from 25.2 to 75.3 degrees C. So I'm making a little note of all the information we're given here. So the change in temperature we can work out is going to be the 75.3 minus the 25.2, which gives us 50.1. So of course we know the specific heat capacity. So straight away here, I can see that we're asked to calculate the enthalpy change of combustion of this alcohol. Now, a lot of people, I'm going to give you a little bit of advice here, a lot of people see that phrase, enthalpy change of combustion, and immediately get tempted to do a Hess cycle. But for a question like this, it's all about what data you're actually given. And here, just alone, the fact that we're given the specific heat capacity of water is enough for me to know what method I need to take next. So whenever we have a question like this, where we need to find enthalpy change of any reaction and we're given the specific heat capacity, we're going to say that Q equals mc delta T, and then we're going to say that delta H is equal to Q, that heat energy, divided by the moles of whatever fuel enabled that reaction. So first things first here, let's work out what Q is. Now Q is a heat energy, and that corresponds to the mass of the water. So in this case we have 150 grams times by the specific heat capacity of that water times by the change in temperature. And this is going to give us an energy in joules. Now, because that's in joules, we are going to want to convert that into kilojoules, because as you can see on your answer line here, enthalpy change is always given in kilojoules per mole. So we're going to want to divide our Q by 1000 to work out what Q is in kilojoules. So then once we have what Q is, we're halfway there, and we can now get to work on working out what delta H actually is, which is what the question wants us to find. So that's Q divided by the moles, and it's the moles of the alcohol or whatever fuel it is that enabled that reaction. So to work out the moles, we know that will be the mass of that alcohol divided by the MR of it. Now we know its formula, and so we can work out the MR by saying, well, we have 6 carbons, so that's 6 times 12, plus 12 plus 16 for the oxygen. So that ends up giving us an MR equal to 100. So the mass here is 4.40, and we will divide that by 100, and I end up getting there 0.044 moles for our number of moles of the alcohol. So now, if we go back to that equation, we know that delta H equals the Q in kilojoules divided by the moles, and we end up getting, we're nearly there now, an answer equal to 713.9 kilojoules per mole. Now there's one last thing, and it's painful to think this is just a 3-mark question, and look at all the work we've just done for it. But the thing that we want to do is to think, okay, enthalpy changes can be positive and they can be negative. Now in this case here, we can see that we have an increase in temperature. And whenever we have an increase in temperature, we know that that must mean that it's an exothermic reaction, and exothermic reactions have a negative enthalpy change. So for our final mark, we want to stick a little negative in front of our enthalpy change. So our final answer here is minus 713.9. They haven't said how many significant figures. I would always recommend after every calculation question, you just go back and review the question one last time to check if you've missed anything. But here, that is absolutely perfect. So for the next part of this, we're asked to write an equation for the complete combustion of alcohol B. And complete combustion, generically speaking, is always some sort of fuel plus lots of oxygen makes carbon dioxide and water, and it will always be like that. Now though, we know the specific fuel, so we want to do this again, but balance it as well. So we've got C6H12O plus O2 makes CO2 plus H2. So to balance this, the very first thing that I would do is I would look at how many carbons there are and then times up the carbon dioxide by that number. So here I'm going to have 6 CO2s. Then if I look at the fact that I have 12 H's in our alcohol and I have H2O, I'm going to times that through by 6 as well to get the 12 hydrogens. Then though, we need to tally up, well, how many oxygens do we now have on each side? Because that's the last thing that we have to balance here. I can see I have 12 oxygens out of my 6 CO2s. I have 6 oxygens in my 6 H2Os. And then over here, I know I've got 1 in my alcohol. I'm not going to count how many oxygens in the O2 yet, because that is the perfect thing to use as our balancer. So in total here, I know that I have 18 and I have 1 on the alcohol on the other side, which means I need to get 17 from my O2. Because it's O2, we're going to halve that number. So the balancing number for the oxygen will be 17 over 2. Or instead you could write that as 8.5. Or instead you could just multiply everything through by 2 here. So we're going to have, in this case, the C6H12O plus 17 over 2, O2, makes 6 CO2s plus 6 H2Os. But do be aware, when we write like that 17 over 2, you could write that as 8.5 as well and still get the answer. Or alternatively, you could just double everything through. So let's have a look at the next question. So we're still within this enthalpy question, but this time we're asked to determine the enthalpy change of combustion indirectly by using the standard enthalpy changes of formations. And here you can see in this little table, we've been given a load of different enthalpy change of formations. Now this now is different, okay? This is now a Hess's law question. Again, it's all about what data they give you. In this case, they have given us the enthalpy of formation numbers, which means we're going to use a formation Hess cycle. So this is where what just came before is going to come in handy, because we've got our balanced equation, haven't we, for the combustion. Now, one thing to note here is, of course, combustion, enthalpy change of combustion, is all about the enthalpy change when 1 mole of a fuel is completely combustion in an excess of oxygen to form carbon dioxide and water. So if you did have the balanced equation with, say, 2 alcohols or something, now you do want to have it so that you have 8.5 or 17 over 2 oxygens. You would then want to halve that to actually get the correct answer here. So if we write what we had as our balanced equation, so we had C6H12O plus 8.5O2 makes 6 CO2 and 6 waters. So we've got our balanced equation there along the top. On the bottom, because it's enthalpy change of formation, I'm going to write the elements, and to be honest, I'm just going to write elements because this is really just a learning prompt, something to help us get the maths right. And you don't have to literally write every single element on the bottom. But standard enthalpy change of formation states that from their elements you can form each of these compounds, okay? So I'm going to do my arrows going up from the elements to these substances. So now that I've got my Hess cycle and it's all looking very, very nice, I'm going to start to go to each of the individual values and fill them in my diagram. So I know that I'm forming one C6H12O, so I'm just going to have minus 348 there. Then on the other side, I know that I am making 6 CO2s, so I'm going to do 6 times minus 394. And also I know that I'm making 6 waters, so I'm going to add on to that 6 minus 286s. So here I have filled in all of the relevant information. So this is where anywhere that I can tidy up the maths a bit, I probably would, okay? So I would, on this bit here, put this into my calculator to get a number, okay? And when I do put this into the calculator, I get minus 4,080. On the other side, we've got this minus 348. That is just on its own. You're not adding anything to it. You're not multiplying it by any number. So that just sits there happy and fine. So now we're nearly there. So I like to think of these for the last step to imagine we're going from like this start point to this end point. Now we could just go direct, couldn't we? We could just go boop, beginning to end. But no, we're going to use Hess's cycle to do that. Remember, Hess's law states that the enthalpy change is exactly the same regardless of the route you take. So if we were to still start at that same start point, but instead we're going to like squiggle our way down this road and then squiggle our way up this road, I will still go from the same start and end at the same end point. So what I would want to do here then is state, okay, I notice that in this first bit here, I'm going in the opposite direction to the pink arrow, aren't I? So what I'm going to do there is I am going to use the opposite sign. So if I was going up from elements to the top, I would use minus 348. But because we're going down instead, I'm going to do 348 without the negative. And then my next squiggle on its way up is in the same direction as the pink arrow. So I'm just going to plop that down exactly the same. And then I will now just put this into the calculator to get the final answer. So here I end up getting minus 3732. And that there will be our final answer. That's an enthalpy change of combustion. I would expect it to be a negative number, so I'm very happy with what I've got there. And finally then, I would just go minus 3732 kilojoules per mole is our answer. Perfect. Well, I hope that made sense. That's a method that I really like. I feel like it makes a lot of sense to sort of visualize it in that way. Because the thing is if you memorize a certain technique, it's going to be slightly different for combustion, which is why I prefer to sort of understand it in this level here. But let's have a look at our next question then, question 5. Okay, so pentammonol can be oxidized by using acidified potassium dichromate. A sample of the reaction was studied using infrared spectroscopy, and we saw that the IR spectrum did not contain a broad absorption in the region 2500 to 3300. What does the absence of that broad absorption tell us? So what that tells us, if we look at our data sheet, so next to the periodic table you'll see a little data sheet for infrared spectroscopy, we will see that it does not contain an OH group belonging to a carboxylic acid. So it does not contain an OH of a carboxylic acid. And it's important that we do refer to it as an OH belonging to a carboxylic acid because it is different, okay? So, looking at 5.2, how would we then carry out this reaction using distillation or reflux? Well, we know that at the end of this oxidation, we don't make a carboxylic acid. But we also know that we start with a primary alcohol. So because we're starting with a primary alcohol, but we're not fully oxidizing it to make a carboxylic acid, we do not want to reflux it. We only want to partially oxidise it, which means we want to use distillation. So in terms of our answer here, I would state that we have a primary alcohol that we only want to partially oxidise. So we have a primary alcohol that we only want to partially oxidise. And that's really important. So we want to use distillation, and that's because distillation removes the more volatile components, therefore preventing any further oxidations. So this is because this process, distillation, removes the most volatile components. So it removes most volatile components, and that prevents any further oxidation. And it is that further oxidation that would in turn end up making a carboxylic acid, which we don't want. Okay, so I hope that that made sense there. It's really important that we get clear on the difference between distillation and reflux and when we use it, as well as having a go at drawing the apparatus and being able to label it. All of those things we might see in an exam question, so do review that if you're at all shaky on this topic. Okay, so hydrocarbons are used as fuels. Kerosene has the formula C10H22. So here they want us to draw 3 branched chain isomers with this formula. So I always like to be quite methodical with these. So I would think normally it would have obviously 10 carbons in a row. So if I just write down a 10 carbon skeletal formula, and we can go from there. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that is 10 carbons. That is the kerosene formula. So in terms of finding branching, I would sort of knock off a carbon from this. So instead have 9 carbons on the chain, and then I can add in a branch along the way. Okay, so I could add in a branch, say here. Now that would give me a branched chain isomer with that formula. So another option is maybe we could knock off some more bits as well. You could just position that particular methyl group we've just added on in different positions as well, and that would work to give us different isomers. Another different isomer that we could have is maybe we could just knock off 3 off of the chain and just have it 7 long, so 1, 2, 3, 4, 5, 6, 7. And then we could replace those 3 carbons that we've taken off in different positions. So we could end up sort of having different ones, say here, here, and here. Of course, it could be in different positions too. This isn't necessarily set in stone, but there's a lot of different versions, to be perfectly honest, that would work for these. Another option, which also had 7 carbons in the chain, is you could branch off with, say, a carbon, and then that can branch off to another couple of methyls as well. Basically, the moral of the story is there's many, many, many different options here that will still give you these branched chain isomers that have that formula. So long as they're skeletal formulas, because of course they explicitly stated you need skeletal formulas, and you do have this branching within it, then you will get the marks, okay? So now we need to write an equation for the complete combustion of C10H22. Now, a bit like a couple of questions ago here, complete combustion is you have that fuel, in this case that's C10H22, you add an excess of oxygen, and then carbon dioxide and water are made in that combustion reaction. So the first thing that I would do to balance this would be I would balance the carbons. So I'm going to add a big 10 in front of the CO2. Next thing I would do is balance the hydrogens, and I can see I've got 22 in this kerosene, and I've got H2 over as one of the products, so I'm going to make 11 of those. And now I want to work out, well, how many oxygens do I need? So if I tally up how many I have over on this product side, I've got 20 from the 10 CO2s, and I've got 11 from the 11 waters. So that gives me 31 in total. And that will therefore mean that the number of oxygens that we need is going to be 31 over 2, or you could write that as 15.5. So that there is our answer to this one. Perfect! So that's great. That is our answer to that part 2. And then over on the next page, we're asked quite a big question. We're told that petrol and diesel are hydrocarbons which are used as fuels in transport. When petrol burns in an internal combustion engine, the exhaust gases contain nitrogen monoxide, nitrogen, carbon dioxide, carbon monoxide, oxygen, and also some unburnt hydrocarbons. So to overcome this problem, cars are fitted with a catalytic converter, and that catalyses the exothermic reaction between nitrogen monoxide and carbon dioxide to form less harmful gases. And that catalyst also increases the rate of reaction. So here we're asked to use an enthalpy profile diagram and a Boltzmann distribution model to explain how the use of a catalyst increases the rate of a reaction. So here the question just says the rate of a reaction. They don't specifically reference this one, although of course you could if you wanted to. So let's start with our enthalpy profile diagram. So here what we want to do is demonstrate how a catalyst affects a reaction using this enthalpy profile diagram. So first things first, I would make sure that we include any axes that are labelled on this. So in a enthalpy profile diagram, we're likely going to have our reactants and our products. We will have an activation energy, which can be labelled here as the activation energy without a catalyst. And we will include here how it looks different when there is a catalyst. So when we do have a catalyst, that bump is going to be less high. So here we will have the activation energy with a catalyst. And you can see there that the activation energy is much lower when you have a catalyst. So we can label everything on the same. We've still got the same enthalpy change. Let us quickly just label on the axes as well. So we've got the enthalpy is here on the y-axis and the progress of reaction is down below here. Okay, so that there sums up how a catalyst affects a reaction in terms of its enthalpy profile diagram. So next though, we need to do a Boltzmann diagram as well. So again, let's start by labelling the axes in this case. So we've got the number of molecules is on our y-axis, and along the bottom we have got the kinetic energy of those particles. So what a Boltzmann distribution model looks like is something along these lines. We have a line though that represents the activation energy. That's just here. And that will be, let's say, our activation energy without a catalyst. And this little region here are the number of molecules that have an energy which exceeds that activation energy. So, on the other hand, when we do have a catalyst, what that does is it lowers that activation energy. And therefore, we have all of these extra molecules, this pink region here, they're the extra molecules that can now take part in that reaction because they all have an energy exceeding the activation energy. So this is the activation energy with a catalyst. So this little shaded region here is the extra molecules with energy above the activation energy when a catalyst is added. So those wouldn't have taken place in the reaction if it wasn't for the fact that a catalyst had been added. But that's perfect though. So that is our Boltzmann model, and you can see that they both really give us a lot of information as to how a catalyst can impact on a reaction. Excellent. If you don't know those already, get them memorised because they will come up again. That's great though. Let's have a look at the next question. So here we're given a few different structures, and we're asked to draw the structure in 6.1 of alkene C. So we're told that it's 2-methyl 2-butene. So I suppose the very first thing that I would do here is I would just show a butene. Okay, so I've got 1, 2, 3, 4 carbons in a row because it's butene. And I know that it's 2-butene, so I know that it's going to have a double bond on the second carbon. And I also know that it's 2-methyl, so I also know that on that second carbon, it is also going to have a methyl group as well. So now that I know that, I can draw the structure of this alkene. So I'm going to say that it is a C double C in the middle, and then, of course, sort of filling in all of the relevant hydrogens. It's going to have a CH3 coming off of one of those carbons. It's going to have a CH3 also coming off that carbon. It's going to have a hydrogen coming off of the other carbon of that double bond, and then a CH3 coming off of the other one. And that is the structure of alkene C. So alkenes react with HBr to form alkyl halides. Draw the major and minor products when alkene C reacts with HBr. So let's just draw it out again how we had it. So here, see the H and the Br will attach to each carbon of that CC double bond. Now the major product of the two will attach to the carbon that has the most other groups attached to it. So the major product will see the bromine of that HBr attached to this first carbon because it has 2 CH3 groups attached to it. And that doesn't have to be CH3s, it could be alkyls, whatever. It is the order of that carbocation that forms that makes the difference. And so on the other one, you see it's only got 1 CH3 attached to that carbon. That's lower priority then, and therefore we're going to see the bromine attaching to the carbon that has the most extra groups attached to it. So, like I mentioned, we know in these cases that we break open that double bond, and we know that each the H and the Br will attach to each of those carbons, but the only difference between the minor and the major is that in the major, your halide ion attaches to the carbon of that CC double bond that has the most other groups attached to it. So here, for the minor product, I'm going to attach instead the H to that particular carbon and the bromine to the carbon of the double bond that has the fewest additional groups added to it. Perfect though. Done. So now we're asked to draw the intermediate that leads to the formation of the major product. So we might as well just recap curly arrows with this, to be fair. So if we imagine that we have our HBr and the Br is our negatively charged side and the H is the positively charged side. And let's go in with our curly arrows. So the double bond is going to attack the H delta plus, and then the bond between the H and the Br is going to go to the Br delta minus. In doing this now, you've broken the double bond, you have attached the H to one of those carbons, and you've broken apart the bond between the H and the Br. So we end up getting here, and remember we're looking at the major product. So we said that the major product has the hydrogen attached to the carbon with the fewest number of groups, leaving a carbocation on the carbon with the most additional groups that aren't hydrogen. So if we were to finish this mechanism, we would then go on over from our negative Br minus to that carbocation, but we didn't need to do that for this question. We just needed to show that carbocation. So adding on all of these little groups, we can see that we have the carbocation attached to the carbon with the 2 CH3s. So here we want to write the name of this alkene B. So let's have a look at what alkene B looked like. Alkene B is this ring and a double bond attached to a group off of that ring. So here, because we have a ring and it's 6 carbons in that ring, it's going to be a cyclohexane. There's no double bonds, so it's hexane in that ring. But of course it does have a double bond, doesn't it? And that double bond is attached to like an ethyl group. So because it's attached to an ethyl group, it's not quite ethyl because it has a double bond. We could call it ethenyl cyclohexane. Or alternatively, we could reverse the way that we sort of name this and instead go with cyclohexyl ethene. Both of those would be absolutely great answers. Okay, so now we're asked to draw the product when alkene B reacts with HBr. So what will happen here is that double bond will break, and what we will have is the ring will now be attached to that bromine and a CH2CH3. And that there is the product that we make. Perfect, so that is good work. Let's have a look at the next question. Okay, so here we're told that many alkenes show EZ isomerism. Draw the E isomer of alkene A. So what I'm going to do first of all here is just sort of draw out so that we've got it for reference what that alkene is. So we've got CH3, a CH2, a C, a double bond CH, a Br and a Cl. So it's written in a very non-standard way that we're probably not very familiar with. And so, as I say, whenever we have anything with alkenes and a mention of cis-trans or EZ isomerism, and also for polymers, I would always start by just writing that central CCC and then kind of make it look a bit like we would if it was a case of ethene. So I'm going to now say, okay, so I had that carbon, I have got a bromine coming off of it, and a hydrogen coming off of it. And then over on the other side, I have got like a CH2CH3 coming off of the other carbon and a Cl. So we want to do EZ isomerism here. Now the issue is that obviously every one of these is different. So we do actually have to return to our standard, how does EZ isomerism work? It's not quite as simple as cis-trans, where cis-trans will always have like a similarity on the left and the right. There'll be something to compare. Say there'd be an H on each side that we could sort of use as a reference point to see if they're on the same side or the opposite side. Now here what we have to do instead is sort of rank this. So we've got hydrogen, which has a mass number of 1, and bromine, which has a much larger mass number of 79.9, I believe. And out of those two, what you want to do is kind of rank it. We need to ask ourselves, well, which of these is, say, the smallest or the biggest of those two? And if we go for the smallest, we'll say, well, hydrogen is the smallest one. Then on the other side, we have this ethyl group and chlorine. And the important thing to know is that we don't, say, add up the whole mass of this ethyl group. Instead, what we're going to do is to look at the atom that it's directly attached to. We only look at further bits down the line if there's an issue with that. If something else is also just attached to a carbon, then we'd sort of go on to the next stage. But here, see, we've got this carbon, which has a mass of 12, and we have got chlorine, which is 35.5. So out of those two, we can see what carbon is the smallest of the two. So just like we said that H was smaller than Br, we're going to say that this ethyl group ranks lower than the Cl. So that means that here, our two starred lower priority groups are on opposite sides. And that is what an E isomer is. So here you see, that is our answer. So we would write that in our little space and we would have our mark. Okay, so we're told that alkenes are a major source of polymers and we're asked to draw the skeletal formula of but-1-ene. So I personally would probably prefer just to write it out in the normal way first, because I personally always feel more comfortable writing it like this. Some people will feel more comfortable with skeletal formula, and we're all different, and that's great. But I can see here that obviously there's 4 carbons in this chain, so I need a little zigzag that has 4 points to it, 1, 2, 3, 4, and I can see that the double bond is on the first carbon. So I'm going to just pop that there. And you can have this as basically the mirror image, because it doesn't matter if you start from the beginning or the end, it will still be numbered 1 for that double bond. Okay, so next we're asked to draw the products formed when but-1-ene reacts with HBr. So this is an addition reaction because we have this double bond. We're going to break open that double bond, and the H and the Br of that HBr are going to attach to each of those carbons. And the reason why they say products is because you can get one where the Br attaches to the first carbon and one where the Br attaches to the second carbon. So in this case, I would again have my 4 carbons in a row. But for my first addition reaction, I'm going to show the H attaching to the first carbon and the Br to the second. That's our first option. And then in addition to that, we could add those on in the reverse way, where the Br actually attaches to the first carbon and the H attaches to that second carbon. And those will be our 2 products formed when but-1-ene reacts with HBr, both of those addition reactions. Perfect. So do remember that you could write that in different ways as well. You could have done it more abbreviated with CH3s and CH2s and so on, or you could have done it with skeletal formula. So long as it gives you the right outcome, then we are all happy and it is correct. All right, so let's have a look at the next question then. So here we're told that but-1-ene can be polymerized, and we're asked to draw the section of the resultant polymer showing 2 repeat units. So this is here where I would use my special trick, where I would start by just drawing regular old butene, and then I would have a go at making it look a bit like how I would draw my ethene. Obviously it's not ethene, but what I mean by that is you've got this central C-double-C bond with these 4 arms coming out of it. And those arms are going to be determined by what is added to those carbons in the normal structure. So that first carbon, I can see it's just got an H and an H. So I've just filled those in. And then on the other side, I can see I've got an H attached to that carbon, but also this big bit here, I also have an ethyl group. So now once I have that monomer written in that way, I can very easily draw repeat units or polymers simply by opening up the arms of this, straightening everything up so it goes straight up and straight down. And in this case here, they want us to do 2 repeat units. So in that case, if I do 1, I would take these 2 carbons and open up their arms, open, open, and then everything else around it, I'm just going to put above and below those 2 carbons. And because here they wanted 2 repeat units, I'm just going to attach directly onto this another one. So I've repeated it twice, but it is the same structure. Next, they want us to give the name of this polymer, and simply because this is an addition polymer, they're named very simply, we just need to take the word poly and put it in front of the name of the alkene. So it's simply polybut-1-ene. Okay, so PVC is a polymer made from the monomer unit vinyl chloride. PVC is hard and brittle. Plasticizers are added to PVC to make them more flexible. Briefly explain how plasticizers make PVC more flexible using your knowledge of intermolecular forces. So here what we want to talk about is the fact that when we have PVC, it has a CCl bond. And the CCl bond in PVC is actually polar because of course the chlorine is more electronegative than the carbon. This means that we end up getting dipole-dipole attraction between these polymer chains, which means that they're going to end up being attracted to each other, you're going to have bonds forming, and that can make pure PVC quite hard and brittle. So we've got this dipole-dipole attraction between the polymer chains, which as a result leads to it being quite hard and brittle. So that would be what our standard PVC is like, okay? It's got these polar bonds, which leads to this dipole-dipole attraction, which in turn makes it hard and brittle. Now these plasticizer molecules can fit between the polymer chains. And what that has the knock-on effect of doing is it disrupts those bonds. It separates them and stops us forming such strong intermolecular forces. With intermolecular forces, like many bonds, it's all about proximity. So if it can't be quite as close to each other, these different molecules, then the bonds formed between them is weaker. So plasticizers, they fit between the polymer molecules. This separates them and in turn weakens the intermolecular bonds. So remember we said that the presence of those intermolecular forces is what made the PVC quite hard and brittle. So by adding these plasticizer molecules, which keeps them apart and weakens those bonds, it's not going to be as hard or brittle, and in turn it will be more flexible. So more flexible. Perfect. So that one there is really just testing us and our knowledge of how plasticizers work. So if you're unfamiliar with that, do make a little note of it, add it to your revision notes, make a flashcard. All these things will help make sure that you don't forget it for next time. Plant oils contain unsaturated hydrocarbons. Part of the structure of an unsaturated compound in plant oils is given below. Draw the displayed formula of the E isomer of this part of structure. So this is where I'm going to get out my classic, let's put everything in terms of that standard ethene structure with my central C-double-C bond and my 4 little sticks coming out of it. And if I look at this structure, I can see that obviously I have the carbon of the double bond, and I'm also going to have a hydrogen. So one of these is going to be hydrogen, and then also this CH2, whoops, I should have used a highlighter. CH2, but with a little line attached, okay? Don't forget that, because what that is us telling us that it's actually ongoing, it's like a polymer. So you might want to write it like that, or we could in turn just do it the other way around. CH2 with a little stick, but that's absolutely fine. So then over on the other side, you can see that again we have an H, and then we also have, again, the same as before, this CH2. Now, we want to do the E isomer of this. So before we dive in and just write them down, let's remember what an E isomer is. So E isomers are when the common groups are opposite each other. So when we want to put the H on next, say, let's put it opposite the position of the original X that we wrote down. And the same for this CH2 with a line attached for the bond. That there is going to be exactly what we need for the E isomer of this structure. So explain why this part of the structure shows E said isomerism. And this question is almost asking us in an indirect way to define why alkenes show isomerism. So for this, I would state, so for this 8.2, I would say it has a C-double-C bond, which of course restricts rotation. So it has C-double-C bonds which restrict rotation. That isn't the only reason though why this has EZ isomerism. If it did just have C-double-C, there are still some cases like that of ethene that actually doesn't show isomerism. And that's because it also needs to have 2 different groups attached to each carbon of the C-double-C. So here we can see that is the case. It has 2 different groups attached to the C-double-C, to each carbon of the C-double-C. Perfect. So that there is our reason, and that is our explanation. So bromine reacts with alkenes even though bromine is a non-polar molecule. Explain why bromine molecules react with the above compound, so this alkene. So the explanation for this is the fact that that C-double-C is very electron rich. So because it is very electron rich, that means that it is able to polarize the bromine. So it's able to polarize the bromine. Now just to remind you what that means, it means that because you've got this very electron dense, electron rich C-double-C, when the bromine gets next to it, the electrons that lie within its bond, so that pair of electrons which normally would be sitting in the middle of that bond, they're going to get repelled away from this electron-rich region, going right towards that far-away bromine. And that makes the bromine of that Br2 that is closest to the electrons to be the delta negative bromine, and then the one which is furthest from the electrons is our delta positive. So that has now polarised it, and we now have an ability to do this reaction. So that there applies for any real sort of non-polar molecules. They can have a much larger likelihood of reacting with that C-double-C bond. So that's like any of the halogens as well are able to react with an alkene to make like a dihaloalkane, and that is because of this reason that the C-double-C bond is very electron rich and therefore it's able to polarize those bonds. Perfect. Well, I hope that made sense, and I hope you're feeling confident. We have now finished section A of this paper. So now we have the next section, section B, which is all about the multiple choice questions. So let's dive into that and see how we get on, okay? I'll see you at the next question. Okay, so section B, what is the name of the alkene monomer required in the reaction that makes the following polymer? So here we need to ask ourselves, well, what is the repeat unit basically, okay? If we were to sort of keep doing this again and again, what would the repeat unit be? So we need to remember that, of course, alkenes make these addition polymers. So they involve the opening up of arms. So here, when we sort of highlight out the region which will be the repeat unit, of course, we've got this little region here as well. So that additional little bond that I've just drawn on, let's do it in a different colour, that is going to come via that opening of arms that comes from a double bond. Okay, so that's not necessarily a part of the monomer in its own right, but it's going to have come from the opening of the arms to then attach to the next monomer. So in this case here, what I have is I have 1, 2, 3, 4, 5 carbons. So straight away, I'm assuming it is going to be a pent, not a butte. And then we need to think, well, which carbon has the double bond? And so in this case here, I can see from the fact that that double bond opens up on carbon number 2, I'm going to say that it is pentuene. So our answer to the first question here is C, pentuene. So next in question 10, we've got a little calculation question going on. So we're told that we have a certain amount of but2ol prepared using 2-bromobutane. Okay, so we're told that we have a mass of 3.552 grams of butan-2ol made using 2-bromobutane. We're also told that the percentage yield is 80%. And we need to go backwards and work out then, well, what mass of 2-bromobutane was used? So to do this, the way that I would start it is I would work out how many moles we have of that alcohol. To do that, we need to work out what the MR of butan-2ol is. And the formula for butan-2ol is C4H9OH. And so the MR then ends up being 4 times 12 plus 9 plus 16 plus 1, which ends up giving us a value of 74. So we know that the MR of butanol is 74, and the moles then will be equal to 3.552 over 74. Ends up giving me a value, surprisingly nice, of 0.048. So this is where we need to take into account the fact that the percentage yield is equal to 80%. So normally the way we would work out percentage yield would be the actual yield over the expected yield times 100, and we get the percentage yield, which in this case is 80. Now we've worked out the actual amount. We know the actual moles. We know that that is actually equal to 0.048, but we need to find out the expected amount of moles. So we can rearrange this to find the expected amount. So the way we would do that is first divide through by 100. So then we'd get 0.048 over that expected equals 0.8. Now to rearrange this to get the expected amount of moles, we are going to do 0.048 divided by 0.8. And that gives us an expected amount of moles equal to 0.06. So we now know how many moles we expect to make of the alcohol. And looking at this reaction, I can see it's a 1-to-1 ratio. So that means that I know that the moles of the 2-bromobutane will be the same. It's also going to be equal to 0.06 because of that 1-to-1 ratio. So we're nearly there now, okay? We need to find the mass of it. The mass is equal to Mr. Moles, MR times the moles. The MR, they have been generous at last to us. If you look at the question, they have given us the MR of the 2-bromobutane. So we can say that is 136.9 times by 0.06. And if we multiply those together, I make the mass of the 2-bromobutane to be 8.21. And that is A. Hurrah! So for every quick question like 9 was in a multiple choice, there will be one that takes a bit of working, like question 10. But don't be disheartened by it, just get on with the maths, just get a pen in your hand and start doing it as quickly as you can, okay? Okay, so which of these two alcohols are structural isomers of each other? So structural isomers have the same molecular formula, but a different structure. So that's what we're looking for in this question. Do they have the same molecular formula? Well, straight away I can see this double bond here, and I can just see that's not going to work. So I've eliminated that. So for the others, let's count how many carbons they have. So I've got 1, 2, 3, 4, 5, 6. This one here has 1, 2, 3, 4, 5. So straight away, even without counting the final one, I know that these two don't match. So we just need to count D's one and see, well, does that have 5 carbons or 6 carbons? So here I've got 1, 2, 3, 4, 5. So I have 5 carbons there. So my answer for the isomers of each other would be A, C and D. Okay, so what is the bond enthalpy for the HI bond in the following equilibrium? So with bond enthalpy, the enthalpy change is equal to the bonds broken, or the enthalpy of the bonds broken, minus the enthalpy of the bonds made. So here what we need to do is to add up all of those bond enthalpies of the broken bonds. And here I can see I just have an H to H and an I to I out of the bonds broken. So that would just be the sum of the 4, 3, 6 belonging to the HH bond and the 1, 5, 1 belonging to the II bond. And then I'm going to subtract it. Then I'm going to subtract from that the bonds made. Now that's the tricky bit because we don't know what that is, but we do know that there's 2 of them because we've got 2 HIs. So I'm going to write 2 HI here, and then we know that that equals the enthalpy change, which in the question they've given that to us, okay, so minus 9. So now this is where I would just get to work in tidying up the maths of this. So if I did do 436 plus 151, I end up getting 587, okay? So I've got minus 9 equals 587 minus 2HI. Now I'm just going to rearrange this, all right? So I'm going to subtract the 587 from minus 9, and I end up getting minus 596 equals minus 2HI. Here we need to divide through by this minus 2. So divide by minus 2, and I end up getting that the HI equals 298. And you can see here that that is A. I will say though that we could have gone 50-50 really quickly because bond enthalpies are never negative, so we could have immediately eliminated B and D and just been left between A and C. And that is the useful thing about multiple choice questions. You know if you've gone wrong somewhere because of little things like that. Let's try 13 though. So what is the process by which liquid hydrocarbons can be converted to gaseous hydrocarbons? Well, if they're liquid, they're basically longer chain hydrocarbons, which therefore have a higher boiling point compared to gaseous ones, which are normally amongst the shortest ones. So the process where we can take a longer hydrocarbon and turn it into a shorter one is simply cracking. That is something that you certainly learnt about back at GCSE, so it should be quite familiar to you. Okay, so which of the oxides of nitrogen is not a common pollutant? So in this case, we might not be too familiar with this, but certainly some of these you would have heard of. All these nitrogen oxides, NO, NO2, N2O, all of those are very common pollutants for nitrogen oxides. The one which isn't is N2O5. So our answer for question 14 is A, N2O5. So for question 15 now, we're asked to put these halide ions in order of their increasing ability to be nucleophiles. So here I would say it's worthwhile remembering, well, what is a nucleophile? So a nucleophile is an electron paired donor, isn't it? And if it's an electron paired donor, we need to ask ourselves, what is going to make it more easy to donate an electron? So if something had more shells, there would therefore be a much weaker attraction between those electrons and the nucleus. So if we're talking about donating electrons, we want to remove electrons from these ions. And to make it as easy as possible to remove these pairs of electrons from these ions, we want to have a weakest attraction possible. So like we said, the more shells that this could have, the weaker the attraction with the nucleus. So weaker attraction between electrons and nucleus, and therefore it will be easier to donate electrons. Easy to donate electron pairs. So there then, what we could think is if we look at these and ask ourselves, okay, so we'd start with chlorine at the top, then bromine, then iodine. We can see that there are more shells as you go down that group. And we said, didn't we, that the more shells there are, the weaker the attraction between the electron pairs and the nucleus, and therefore the easier it will be for them to donate electron pairs. So here we could say more nucleophilic as it goes down. So out of these then, in order of increasing nucleophilicity, it is going to be B. Again here, I think we could 50-50 that quite easily, because in terms of trends, it doesn't make any sense for the trend not to go in that order of down the group or up the group. So I would say that we could have eliminated here C and D quite easily. And then it's just a case of asking ourselves, well, which is going to be the most nucleophilic or the least nucleophilic. So next we're asked, what is the shape of the CFC CF2Cl2 molecule? So in this case, what would be helpful to know is it's going to have a structure very similar to methane. Carbon, of course, it has 4 electrons in its outer shell, and fluorine has 7. It needs to gain 1, so you will end up getting fluorines looking somewhat like this to get their full outer shell, and the chlorines would do the same too. The ins and outs of that aren't as important as the fact that surrounding that carbon we have 4 bonded pairs and no lone pairs. And whenever we have 4 bonded pairs and no lone pairs, we have a tetrahedral structure. So that is the answer to 16, it is tetrahedral. Okay, so how many moles of oxygen are required for the complete combustion of 1 mole of pentane? So here really we just need to do a balanced equation, and this is complete combustion. So we have pentane first off. I guess the first thing they're asking us here is, can we recognise the formula for pentane? So pentane is C5H12, and we are going to add on our oxygen, and we will end up making carbon dioxide and water only because we have complete combustion. So now we need to balance this. So we have 5 carbons, so we need to have 5 CO2s, and we have 12 hydrogens, so that means we need to have 6 waters. And now it's just a case of balancing up. So we had 10 oxygens within the 5 CO2s, and we have 6 within the 6 H2Os. So that tallies up to make 16. So we need to have 8 O2s. So our answer for 17 is C. The next question is question 18, and we're asked to put these in order of their increasing bond length between the carbon-carbons. So here we're asked to put them in increasing order of C-C bond length for these compounds. So we need to recognise what we have here, And when we have C2H4, that is going to be a C double C bond. When we have C6H6, that's actually a benzene ring. And when we have C2H2, that will actually be a C triple C bond. And what we need to know here really is the more bonds there are, so say a triple bond compared to a double bond, the shorter that bond will be. So out of all of these, C is the shortest of all those bonds, so therefore B will be your answer. Now I guess benzene, that benzene ring could be the most confusing bit. And benzene, although you might be thinking, is it like a double bond? Is it like a single bond? It actually has a bond length between the C double C and C single C. So actually that's going to be a longer bond than the C double C anyway. So that just further reinforces our answer, which is B. So the triple bond is the shortest. Then the next one is the double bond. The next one is the benzene's bonds. And finally, if there was another one, the C single C bond would be that last one. So for 19, we're asked how many structural isomers are there with the molecular formula C4H9I. And straight away, I would start drawing a straight chain and I would have a go at putting the I in as many positions as I could. So you can see I can put it on the first carbon of that chain, or I could put it on the second carbon of the chain. There's nothing else I can do with this positioning, because if I moved it onto the third carbon, it's actually the same as the second carbon. But what I could do is I could reduce the length of the carbon chain and put a branch on. So now I can decide, well, where could I put my iodine? So I could put the iodine on the first carbon, which doesn't have any branches attached to it, or I could put it on that middle carbon here. Now anywhere else that I chose to place that would again give us one of the original ones. So actually, that is all the isomers. We can't make it two carbons long, because then it would have a branch that would actually end up being the same as one of the ones that we've already written. So 4 is our answer, so D is what I circle. Okay, so compound Y is an atmospheric pollutant with a molecular ion peak at MZ54. So what that tells me is we have the MR of this molecule. So it showed the following composition. So we know that carbon is 88.89 and H is 11.1. So straight away I'm thinking here that this is going to be something to do with an empirical formula. It also tells me that compound Y reacts with H2 in the presence of a nickel catalyst. Now that is the reaction that we normally have when we are taking an alkene and breaking it into an alkane, okay? So that's hydrogenating an alkene into an alkane. And because it says a 1:2 ratio, that suggests to me that there are 2 double bonds. So there's 2 carbon-carbon double bonds within this. And all of these things are going to help me place this together. In fact, straight away, before I even do anything here, I'm looking at this and I'm saying, well, propene only has 1 double bond, and 2-butene only has 1 double bond, and so does 2-methylpropene. So actually, even without doing anything at all more here, I feel like I can answer it without even doing any of the maths. I would say it was B. But I'm going to show you through the calculation anyway, just to reinforce that. So the mass, or the percentage by mass, we've written them down. I would then do the MRs of the carbon and the hydrogen, and I would then work out the moles of each of those, or at least the mole ratio, because it's not strictly speaking the moles when we're using percentage by mass rather than just actual mass. So for that mole ratio, 7.4075 for the carbon when I divide these by each other, and then I get 11.1 for the hydrogen. So that is indeed a ratio, but we want the simplest whole number ratio. So I'm now going to divide each of those by the smallest number. I'm going to divide each of those by the 7.4075. So if I do 11.1 divided by 7.4075, I get 1.5, okay? Now, that's still not quite a whole number ratio, is it? But if I double them, I get a 2:3 ratio. So I know that we have C2H3 is the empirical formula, and we can work out what the molecular formula is by comparing the MR of the empirical formula to the overall MR given in the question. So the MR of C2H3 will be 12 times 2 plus 3 times 1. So that is 27. And as the MR of the whole molecule is 54, see if I do 54 over 27, I get 2. I know that the molecular formula is double the empirical formula. So it's actually C4H6. So 4 carbons, that supports the butadiene that we have there. So B would be your answer. But please do notice, actually, by understanding the information they've given us, we didn't actually have to do any calculations. Okay, so which compound would show a small n+1 peak at MZ73 during mass spectrometry? Now, the n+1 peaks are normally going to be due to an isotope, okay? So if we were to work out the MRs of these individual compounds here and ask ourselves, are any of the MRs we've actually calculated just one away from this n+1 peak, this very small n+1 peak, which is going to be due just to isotopes? So for butanol, butan-1-ol there, which is C4H9OH, that has an MR of 48 plus 1 plus 17, which is 66. So I'm going to say it's not A because it's too different to 73. So then if we did cyclopentane, so cyclopentane has a formula the same as just pentene. Remember that cycloalkanes have the same general formula as alkenes. So it's just C5H10, which will be 5 times 12 plus 10, which is 70, which is close, but we're not quite there yet. And then if we try it for pentane, so pentane will be C5H12, which will be 5 times 12 plus 12, which is 72. And see, the 73 that we get a small peak of is just one above that. And so isotopes could definitely explain this peak of one above the mass of the standard pentane. So our answer to this one is just C. So finally here, the last couple of questions. Which compound would you expect to have the lowest boiling point? So ethanol, dimethyl ether, water or methane. So all of those there have some oxygens in them which might have polar bonds. Some of them are going to have hydrogen bonds when they have OHs within them. One of these have none of those, and that is the methane. It doesn't have polar bonds, it's just C to H, which doesn't have a significant difference in electronegativity. So methane here is going to be the only example that only has these London forces. These molecules are smaller than lots of the others, therefore they're going to have fewer points of contact. But yeah, the reason that we're going to choose methane here is it only has London forces, whereas the others have some permanent dipole or hydrogen bonds. Perfect, so D. And the last question, which of the following is the correct name for the molecule below? So the method that I like to use for these is I like to trace a pen through the longest carbon chain. So here my longest chain looks like this one. And then I count how many carbons I have. So I've got 1, 2, 3, 4, 5, 6, 7. Now that alone doesn't help us because we see they're all heptane. Fair enough. But we can now get some work on the numbering because we could have numbered it that way or we could have numbered it the other way, okay? If we numbered it this way, see we'd get 1, 2, 3, 4. So you'd get 4, 4 dimethyl, 5 ethyl, heptane. And at first glance, that seems fine. But the issue arises here. If we chose to number it the other way around, so starting with instead the other end as our number 1, notice that when we number it, we can number it using smaller numbers there. So we could get 3 ethyl, or 4 dimethyl, heptane. So there, the fact that we get a lower number out of these is what makes us choose this as our correct answer. So our final answer here is A. So really important that we know that almost the sum total of all the numbers, you have to choose the smallest option when it comes to numbering them. It's not just they're both the same, so it's fine. You do have to actively choose the one with the smallest sum total. Perfect though. Well done for getting through this paper. I can't believe we made it through another one. Keep working, and I will see you at the next paper then. Bye.
Ouch! This is why in some videos I explain scratches.